Okay, well, we're going to be looking at the chain rule in multivariable calculus now. So we know that the chain rule in single variable calculus, for example, I've got some function f of g of x, that the derivative of a composite function, we use the chain rule, is the derivative of the outside, so f prime of g of x, multiplied by the derivative of the inside. Okay, well, very similar procedure is going to be the case for multivariable. But let's try to first interpret what this all means. So imagine that we have corn production, and corn production depends on rainfall and temperature. However, both rainfall and temperature are being affected by time, thanks to climate change. So imagine that we have the following information, that rainfall is decreasing at that rate of 0.2 centimeters per year, and that temperature is increasing at 0.1 centimeters per year. What we want to do is, given that, find the current rate of change of corn with respect to time, given that corn has a partial derivative with respect to rainfall of 3.3 and a partial derivative with respect to temperature of -5. Okay, so just what this means is, as the rain increases a little bit at our current state, our production increases. As the temperature increases, our production decreases. So what we know is that our change in corn by local linearity is our partial derivative with respect to rainfall times the change in rainfall plus the partial derivative with respect to temperature times the change in temperature. But where are these changes in rain and changes in temperature coming from? Well, those are coming from time. And we know that delta R is -0.2 because of climate change. And delta T is 0.1. So temperature is increasing, rainfall is decreasing. Therefore, we could express our change in R as -0.2 times the change in T, and similarly the change in temperature equals 0.1 times the change in time. So we could restate this change in corn equation to being 3.3, which is the change in corn when rain changes, times -0.2 delta T, which is our change in rain over time, -5 from the change in corn production when temperature increases, times 0.1 delta T, which is our increase in temperature. So therefore, given these predictions of my partial change of corn with respect to rainfall and temperature, and my increasing rainfall and temperature because of time, I'm able to get a prediction for the change in corn production over time. All right, so this is we're gonna develop a kind of a more concise method for doing this, but this is the main idea of the chain rule, because what we have is corn as a function of rain and temperature, but rain and temperature are really functions of time. So corn is a function of rain as a function of time, and temperature is a function of time. So it's a chain rule with two variables. All right, so let's think about this. What we just did, is we said, okay, our change in z comes from our partial derivative in z with respect to x times our change in x, and this change in x comes from time changing, plus our partial derivative with respect to y times my change in y, and again that change in y is coming from time changing, so I can replace delta y and delta x, the change in x and the change in y, I can replace those with the following, because they are changing as a function of time. They change because of time. So in other words, the amount, if we think about x, the amount that x changes depends on time, so how it changes with time times the amount of time that has passed. So we are replacing dx with that, and similarly with dy, or delta y. So when we do the replacement, so changing dx into right there and changing delta y into right here, we can substitute out factor out a delta t, so factor that out, and then we're going to divide both sides by delta t. And what we see is that we get delta z over delta t, or let's call this dz dt. So the change in z with respect to time, which comes from multiplying the partial derivative with z with respect to x times dx dt, plus the partial of z with respect to y times dy dt. Okay, so now we're going to build this up a little bit. So first of all, this is what we have right now, and this is when we've got a three-variable system, or a three-dimensional system, three-variable system, where both my independent variables are a function of one variable, in this case time. And we can think about drawing a little bit of a map here. So, we start with our independent variable, and z depends on both x and y. And x depends on t, and y depends on t. So my x value changes as a function of time. And as my x value changes, it changes z, partial derivative. And we've got a partial derivative here because z changes from both x and y. So then, in order to think about our change from z, how z changes because of time, we just multiply down this pyramid. Or not that pyramid, whatever this shape is. So we get that dz dt equals how z is changing with x times how x changes with time. So that's going down this path, and then plus going down the other path. So partial with respect to y plus dy dt. Okay, so that's when our independent variables only are a function of one other variable, in this case time. Let's extend that. However, before we do, let's just do one practice example of this. So we'll do one practice example where x and y are both functions of one variable time. So we can do it the long way, like we just showed. So we have z to x to y to t, and we know that the partial derivative of z with respect to x would be sine y, and the partial derivative of z with respect to y is going to be x cos y, just taking partial derivatives. And then dx dt is 2t, and dy dt is 2. So therefore, we would get that dz dt equals sine of y times 2t plus, so that was multiplying down this line, and then multiplying down this line, plus x cos of y times 2. Now, what you should be thinking right now is, this is a little bit ugly because I've got y's and t's and x's, but we can replace everything in terms of t because we know what x and y are in terms of t. So this ends up equaling sine of 2t plus 1 times 2t plus t squared, because that's x, times cos of y, which is 2t plus 1, times 2. Now, we could have, and let's look at another way of finding this chain rule, and that is, and I'm going to put this on another page here. What we could do is just substitute x's and y's right away and get z as a function of time. So what we could have done is, because of, well, z equals x sine y, which is t squared, because that's x, times sine of y, which is 2t plus 1. And then we're going to need to use the product rule, but what we get is that dz dt equals the following. And both answers will get to the exact same thing. So this was using the product rule. What we did is we substituted x and y, we substituted those values in, expressing x as t squared and y as 2t plus 1, and then we took the derivative using the product rule. And notice, going back a page, that it's exactly the same answer that we got before, as we would hope.
Okay, so now let's just think about this in terms of a general chain rule. So when we have some function in terms of x, y, and then x and y are both in terms of some other function, let's say u and v. So we know that x is a function in terms of u and v, instead of just one variable time. And y is also a function in terms of u and v. So now we've got f changing with x and y, and x and y both changing with u and v. So what we can do is think about, we've got my value f, which changes in terms of x and y. And x and y are both changing with respect to u and v. So if I want to think about, how does my partial derivative of f, or z, let's just be consistent here, we'll call it z. If I want to think about my partial derivative of z, how it changes as v changes. Now these are partial derivatives because there's two variables down here as opposed to time before. The way that z can change as a function of v is it can go x to v or y to v. So it will equal, going down the first half, the partial derivative of z with respect to x times the partial derivative of x with respect to v, and that's how z changes with v going down the x path. Plus, z can also change as y changes. So dz dy times how y changes with v. So we get this kind of multi-part equation here for the partial derivatives because of the chain rule. And here's the diagram that we just drew. So let's look at how that works. We want to compute the partial derivatives of w with respect to u and with respect to v. So if we put w and x and y, and now let's right away compute those partials. So the partial of w with respect to x is 2x times e to the y, and the partial with respect to y is x squared e to the y. And now we have x changing as a function of u, and v, similarly, y is changing because of those. So, just to be clear, let's write everything with x in the x direction in red. So the change in x with respect to v, going here, is 4. With respect to v, it's 0, because there's no v. X is only depending on u. And the change in x with respect to u is 4. And now if we look at our y, we'll continue doing our y in blue. The change in y with respect to u is going to be, looking up here, the change in y with respect to u is 6u, and the change in y with respect to v is minus 2. So if we want to find the partial derivative of w with respect to u, it will equal, so how w changes as u changes. And that is going to equal 2x e to the y times 4, so that's going down this direction, plus x squared e to the y times 6u. Now, what's critical here is that we try to get everything in terms of u's and v's, because we want to think about w in terms of u and v. So we'd have to rewrite this as 2x, where x is 4u, e to the y, where y is 3u squared, so we have 3u squared minus 2v, and then plus x squared, which is 4 times u squared times e to the y, so 3u squared minus 2v times 6u. So it gets a little bit ugly, but that's okay. And then to do the partial derivative of w with respect to v, it would be the same thing, only then you'd be going down these paths. So that's actually a little bit easier to find because of that 0 there. So the partial derivative of w with respect to v is going to be 0 going down that direction, and then x squared e to the y times negative 2 going down this direction. And so just to write that in terms of u and v, it is 4u squared, negative 2, should have been in front, negative 2, and then e to the 3u squared minus 2v. And so these are telling me how w is changing with respect to u and with respect to v, even though we had w being defined in terms of x and y.
Okay, so let's look at some examples here. If we want to find dz dt using the chain rule, where x and y are both functions of t, we know that, so let's just do the first one, dz dt equals change in z with respect to x times dx dt plus change in z with respect to y times dy dt. So just plugging in what we know, partial derivative with respect to x is y squared, and change in x with respect to time would be negative e to the negative t plus partial of z with respect to y is going to be 2yx times the derivative of y with respect to time, so cos of t. So here is how z is changing with time using the chain rule. What about the next one? So again, partial of z with respect to x times dx dt plus partial of z with respect to y times dy dt. Looking at our second equation, so with respect to x, we're going to get 1 over x squared plus y squared times 2x, that's the partial of z with respect to x, times dx dt. So times negative 1 over t squared plus, and the partial of z with respect to y, we're going to get 2y over x squared plus y squared times the derivative of root t. So that's going to be 1 over 2 root t. And then the last step, if we wanted to, we could substitute y's and x's with their t value. We're not going to do 3. Instead, let's do one more problem where we have z as a function of x and y, and x and y as functions of u and v. So just to keep it simple, let's say that z is xy squared, and x is u plus v, and y is u times v. So if I want to find the partial derivative of z with respect to v, the ways in which z changes because of v is that path and this path. So to find that green path, that's going to equal partial of z with respect to x, so y squared, times partial of x with respect to v. That's just 1. Plus, and now we need to do the yellow path. So plus partial of z with respect to y, that's 2yx, times the partial of y with respect to v. And that's going to be multiplied by u. And then if we wanted to write this all in terms of u and v, this would equal uv squared plus 2 times uv, and then x is u plus v times u. And that's telling me how z is changing with v right there.